To you, if you go to the lectures website, you notice that I already posted on Tuesday. So there's some required reading over here. So it's called Point and Point Collector. So you have to read a document about 14 pages or so, but it's like a tutorial document. This is something that you have to know for lab test 2. I'll give you guys some exercise, additional exercises like lab number 1. I'll post it tomorrow, and then I'll let everybody know. That's something you should really try to practice, and I'll give you a solution a little bit later. You can expect the lab test 2 more or less the same. So hopefully this time you get more time to get prepared. Okay, let's go back to where we were, and let's finish first of all the topic about call by reference. Okay, so basically the tricky thing about call by reference is whenever you're trying to make a method call and you're passing an object as the argument, you're not really passing that object directly per se. You're only passing a copy of its address. And I'm going to show you from two different methods where you can see the effects. Something that you might expect to happen did not really occur. Okay, that's where we left off. Let me just repeat this one again. Okay, now let's have a look at, remember we got a utility class over here. Let's consider this mutator method. It doesn't return anything. It's called Reassign Reference. Let's say we have point and Q, which means somehow we're going to pass an object of type points over here. But we're going to see how it's actually going to work. Let's see what the method intends to do, but it may not be exactly what it intends to do. It says that we're going to create a new point object called MP, which is of 6 and 8 as X and Y. And then we're going to reassign whatever we pass over here as Q to MP. Okay, that's what the method is trying to do. Let's try to see what's going on here. I'm going to explain this because already in the Eclipse we have seen that. So let me just use the iPad again and show you. Okay, let's add a new page over here, and let's see. I'm going to just show you the relevant classes and see how this works out. Okay, so first of all, we have the class utility over here, and let's isolate that particular method there. It's called reassign ref. Void reassigned ref, and then we have point Q, and then there are only 2 lines of code over here. We say point MP is assigned to a new point, so we have to create a new object over here in this method. So point 6 and 8, and then we say Q is assigned to MP. Okay, so this is class number 1 that we have to consider. Okay, one thing I want to point out, first of all, when you say point Q over here, what does that really mean? When you declare a parameter of type points, that means what you are expecting is an address. Expecting an address of some point objects. It's really important to notice this first, to know that what we are really expecting is not really an object. We are expecting some address. Okay? And let's see what's going to happen if we try to make this method call. Okay? So now let's do another class over here, which is our unit test. So somehow you have your test method here. It's called test call by reference number 1. Okay, that's the first one. Okay, let's see what it is trying to do. First of all, we're going to create a utility object. We say U is equal to new, and then util. This one is not that important. This one just to make sure we don't really call on the null pointer. And then we say point P is assigned to new point. And over here we put 3 and 4. Let's trace one by one. Up to now, what we have done, we have created in the memory some objects of type points up to now. So it's of type points where we got X and Y, and it has 3 and 4, and P is pointing to it. That's what we have achieved. Okay. Next line. When we say U dot reassign ref, and over here we pass P over here. Okay, notice that. First of all, let's see we are really calling this method here. That's why I'm putting definition there. And then we can see that, let's see again. When I say point Q, I say we are expecting an address. And over here, I'm really passing to you an address, which is P. Because P, again, is an object variable. It does not store any objects. It stores the address of some objects, right? So now here's a tricky thing. So what does it really mean over here? When I say I'm going to pass P as Q, right? What I did before was I will simply just do something like this. But I'm going to just show you again. I'm going to undo that. I say replace every occurrence of Q just by P. And then Q here will also be P, right? That's what I did before. However, what I did before was kind of oversimplify the situation a little bit. So I want you to be very clear about this, okay? Just for this particular scenario. It wouldn't be so correct because if you look in this version here, I have P is assigned to MP. So in some way, I'm trying to say P is going to be reassigned to something else. However, that's not what's going to happen. That's why the confusion might be. Okay, let me just clarify that. Okay, so let me undo. Now I'm going to tell you what exactly really happens. What really happened is when we are expecting an address from Q over here and we're passing P, we don't really pass P directly. It's something called call by reference. We're only passing a copy of P, which means some same address, but it's a different copy. Okay? So what's really happening is here. I'm going to write it down. So what's going to happen is a copy of P will replace every occurrence of Q. Okay? So what really want to notice is it's a copy. It's not exactly just that reference. It's a copy. Okay? So let's see how we can see the diagram here. So if you want to make a copy, it's easy. You just assign the reference. So in this case, it's going to be, you can see that Q basically just a copy of P. So they point to the same objects, but they're separate variables. They just have the same address. That's why they're pointing to the same objects. So now, let's try to go on. So now we know that Q is not, so Q is also referring to the same objects, but it's not exactly just P. It's just a duplicate of P. So now let's continue the rest of the code. Let me use a different color here. What's going to happen if I say this? I say MP is going to point to a new object also of type P, points. And then I'm going to have X and Y, 6 and 8 over here, right? Now the last line over here. When I say Q is assigned to MP in this case, what's going to happen? That means I'm going to, let me choose any other color here. What about this? Okay. That means Q is not going to point to here anymore. Q is going to point to here. So after this code, let's see what happens to P and Q. What happened is Q is pointing to here, the new point that we created, right? And also we have P, which is still pointing to the old objects. So P was not reassigned really. It's only the copy of P that was reassigned. Any questions? That's case number 1. So case number 1, I would say is more confusing than case number 2. So make sure you understand case number 1. Okay? So if you look back to the JUnit test, what I'm really testing over here is to make sure, even if I pass P over here for this method here, but after the method call, P remains the same. P is still pointing to the same objects over here. It does not point to the new object over here. It does not. Okay? Any question about case number 1 before I move on? Okay? Good. Yes?
So right now, if we do like an assert true,
yeah.
P is still pointing to the original.
It's a very good question. So I did do that in the JUnit test. So the way I did it, I'll show you very quickly. You can see that somehow, in order for me to make such assertion, somehow I want to say before the method call, P was pointing to something. After the method call, P is pointing to another thing. We want to make sure the two things are really the same thing, right? So it sounds a little bit weird, but I'll show you. Let's see how I did it. I'll show you very quickly, okay, as a review. So if you go to the project I made available to you, so let me just show you that test case over here. So you can see that the way I did it was, before the method call, I simply just create another point object to say, let's store the old value that P used to point to in this particular variable there. And then after the method call, I simply make sure P is the same as before, basically, right? That's what the test is doing, okay? Okay, guys, any questions before I move on to case number 2? Okay, case number 2 is actually easier, case number 2. As long as you know that for call by reference, whenever you're passing an object as arguments, you're not really passing that object directly. You only pass a copy of that reference, only a copy, okay? Now, case number 3, we're going to illustrate that because it's a copy of the same object, well, sorry, a copy of the same address. So we're gonna have some aliasing effects. So let's see case number 3, okay? So now for case number 3, I'm going to maybe draw a diagram first and then we'll code it up for you. So let's be clear. Okay, for case number 3, let's see. For case number 3, it's going to be something similar. Let me just build a context first. I'll go a little bit faster. So here we got class util over here. So now we're considering a different method. And the method is called change via ref. So we're not trying to reassign the ref. We are trying to make a change using that ref. Via ref. And the argument is basically the same. I say point and then q. And over here, I would say q dot move horizontally. I would say h horizontally by 3 units, move to the right. And then q dot move vertically, move up by 4 units. So these are the 2 lines of code I'm going to show you. Okay, that's class number 1. Now, for class number 2, again, a test. Let's do something similar. Okay, so now we have something called test call by reference case number 2. Okay, of course, still we have to create a utility object first, but let me ignore that line. That line is not really important. So now if I say points P is assigned to new point. Similar setup, but now after this, I'm going to say u dot change via ref, and then I would say P over here. Okay, so now we are trying to make this method call here. Change via ref, change via ref, and we got the same expectation as before. When you say point Q, we are expecting some address. But this address turns out to be a copy of P, okay? So now I'm just gonna make it explicit to you. When we make this method call here, we say Q is replaced by a copy of P, okay? So copy here is really important, okay? Let's draw some diagram here and make sure we understand that. First of all, this line. When we are creating P over here, so it's pointing to a point object here, and that point there has 3 and 4 for x and y, 3 and 4. And now we are trying to make this method call over here. And what's going to happen? Remember now, Q is simply just a copy of P, which means Q is basically pointing to the same objects. So now we do have aliasing. So now what's going to happen when we do this line here? When we say q dot move h horizontally by 3 units, which means we're going to increment the x by 3. In this case, well, it seems that we only got one object here in context, right? And that object is pointing to by both p and q, so we do have aliasing. Aliasing means when you're trying to change the object by one of the references, it's going to be visible by all the others, okay? So now in this case, we're going to change from 3 to 6, right? So that's what this line would do. Another line, let's say this line here, when we say q dot move vertically by 4 units, we're going to say q dot y is incremented by 4 units, so that becomes 8. So now you can see that after this line here, after this, both p and q will have the x and y being 6 and 8. Right? So now, after this method call, I'm going to write some assert here. So now you can say assert true. p.x equals q.x, and p.y equals q.y, and let's make a little bit more. You can say p.x equals 6, and q.y equals 8. Something like that, right? So you can make these assertions. They really refer to the same points. So that's the second case for call by reference, which means you're not really trying to reassign the reference, which is not possible, as we saw in the first case. But in this case, because of aliasing, you're trying to make a change to the object that's being pointed to by more than one references. And of course, the change is going to be visible by all the references involved. Questions about call by reference? Are we okay? If you've got questions, it's now time to ask before I move on. Yes? Yes, yeah. How do you write move h? Okay, sure, no problem. How do we implement h? Maybe I'll just show it to you. That might be, can save a little bit of time. So remember in that code there, it's the point here. For example, move horizontally. In that case, we simply just change the x value of the objects. But now, because p and q, they're pointing to the same objects, so changing one is going to affect the other. Yeah. No? No questions? Everybody happy? Okay. Yes? So basically, okay. When you are passing an object, let me use the example again to emphasize. It's a good question. Okay. Let's say this. When we are passing this object here, let me again emphasize, P over here. When we are passing P, we don't really pass the entire objects that P is pointing to. We only make a copy of P. And P is actually an address, right? We just make a copy of it. And the copy is going to be replacing the actual argument Q. So that's why I'm drawing that P and Q, they are referring to the same objects, right? So now, depending on what you do inside the method over here, in case number 2, we try to make a method call from Q. In that case, aliasing is going to make sure whatever effect you're going to have by Q is going to be also visible by P. In case number 1, it's different. In case number one there, oops, sorry about that. How did I get there? Okay, in case number 1, it's a little bit different. In case number 1, we know that both P and Q, they point to the same objects, right? But now we're doing something a little bit different. We are not really trying to change the object itself. We're only trying to change the address. In this case, you can see that we are trying to reassign Q to be MP. In that case, because P and Q, they are independent copies of addresses. So you're only affecting Q, not P. Okay, that's what case number 1 is illustrating. So what's the lesson to learn from the 2 cases? If you're, because of call by reference, whenever you are trying to make a change through the argument reference there, you should never try to reassign because it has no effects. You should never do anything like case number 1. You should always try to do something like case number 2. Okay, that's a lesson. If we are okay, then we'll move on, right? Okay, yes. Yeah, we're passing an address that is stored in P. Not a copy of the object. It's only a copy of the address of the objects, right? Only the address. Okay. Always remember, when we talk about reference variable, we only store addresses. We never store the entire objects. Okay. Okay. Now, I would like to move on to a new topic, and this topic is about hash code. So I'm pretty sure for lab number 1, sorry, not lab number 1, lab number 3, you have to implement some hash code. But I would say the one you are required to write is actually very easy to write. So I wouldn't worry too much about it. But I think to really talk about hash code, I would like to give you a little bit more complete story. Why do we need hash code? To talk about hash code, we need to talk about something called hash table. But to talk about hash table, you want to know why you need hash table, right? So I'm going to give you some story. Hopefully we can finish by the end of the class, but I think that's worth doing. It's quite a long story, but you'll learn quite many things from there, okay? It will be also very, very good preview for next week. Okay, let me just start with the beginning of the story here, and then. Okay. Oh, sorry, not here. Okay, so now I just want to make sure that's the first slide. Yes. Okay, so now, so the whole topic is going to be about hashing. Eventually, I will get there. But let's just start with something very simple. So let's talk about a map. So you hear people talking about data structure, which we will learn much more in 2011. So let's just get a feel. So a map is simply a data structure. But let's learn intuitively how the map works. Sometimes people say map is a table, like a hash table or a dictionary. So you can just use that interchangeably. So what does a map do? It simply stores something, just like an array. It's going to store a collection of entries. So here the entry has to be defined properly. What do I mean by an entry? The entry has two things together. One is called key, the other one is called value. You got key and value. So now, for example, let's say this is a very real-life example. I'm not sure if you have ever used this, right? So now, basically, you got a cabinet over there. So cabinet itself is like a map. It stores lots of files over there. Each file is like an entry. And each file has two components over there. It has something like a label to say that's a Q2 report. That's a label. And then the file itself is the value. So now, how do I, for example, let's say I want to look for the Q3 report. What should I do? I need to go into the map and then retrieve the one that has the label with Q3 report. So I always search by using the key. And then once I use the key to find out the corresponding file, I can retrieve the value. Okay? That's kind of how the map works. So now let me make it a little bit more computer science-like example. Okay? You can think of it as a table. So now let's say this. It's a little bit like a dictionary. Remember, if you talk about the old dictionary like a book, you actually have to search for the word, for example, university. That's the key. And once you see the university entry there, you can see the definition for what a university is, right? So you got key and value. So now let's focus on the right-hand side because that's the example I'm going to use throughout the hashing example. So now you can see that for entry there, it has two things. It has search key, it has value. In the search key, let's make it easy, just integer. The search key, just integer, can be 1, 25, 3, 14. Okay? You can notice that there's no duplication, right? And it's actually quite important. The search key cannot have any duplicates. Imagine that if in the dictionary, you actually got two words that actually have the same spelling. It'll be very confusing, right? So the search key must be unique. And then for the value there, I simply just say string, like size 1 string. It can be D, C, F, Z, A, C, and Q. Okay? So that's about key and value. Whenever we want to search inside a map, for example, I want to say, I want to find out the value that is associated with the key 6. What would that be? A. Okay, very good. That's good. Okay, so now we talk about entry. So we got value and we got search key. And I'm going to give you some example you're very familiar with already. So each search key must uniquely identify an object in the map. And also, so now here's the thing. When we talk about map, it's only an abstract concept. We haven't talked about how you can code it up in Java. What I would do is I will show you a very naive implementation. And the implementation, you can also find the details from the required reading over there. I'm going to go over that, give you intuition. However, the naive implementation using a single array is not going to be efficient. We say that the computational complexity is way too high. And we're going to improve that. How to improve that? A hash table. Okay, that's kind of how I'm going to build up the story. Okay, just remember that the search key must be unique, and you must use the search key to efficiently. I will define what efficiently means. Formally, maybe next week, but intuitively today. Okay, now let's see some link over here. So now, another way to understand maps, you can think about arrays that you actually use a lot in lab test 1. It's actually also a special kind of map. How do we see that? So you can think about for array, you got indices 0, 1, 2, 3, 4, 5 up to the length -1. These are unique and these are just search keys. By using a particular array index, you can find out what is really stored in the array cell, right? So you got search key and you got value. That's one way to look at that. For example, let's say over here, I have an array which has 3 elements there, A, B, and C. In this case, how many entries do I have? 3. The way you can look at that is I got 3 entries. The first entry there has the key 0, and the value associated with it is A, and etc. That's how you can see the array as a map. Okay, and what else? Okay. So now one thing to notice is the way we access the array index is very fast, the last point over there. Whenever you pass an index to the array, to look up the corresponding element in the memory is very fast. Under the hood, they simply just calculate the address, like offset from the beginning of the array, and try to look it up. You will learn more in 2031. I just want to tell you that if you can somehow use array indexing in your implementation, it's very efficient. Okay? Now, let's go a little bit further. But in general, this is a tricky part. Over here, for simplicity, I give you an array where the indices are numerical. Also, in the previous slides, the table I gave to you, the indices, the keys are also integers. They're easy. However, in general, the keys can be anything. For example, it can be points, it can be persons, it can be strings, it can be anything. So now somehow we have to solve this challenge here to say, given any search key of any type, how can we use that particular key to efficiently look into the map and find out the associated value? So that's really the problem we are facing. Okay? I'm going to stick with the integer, so you can generalize that later. So just give you some example. Let's say for your case, given your student ID, because no 2 students have the same student ID. Given your student ID, you can retrieve the student record objects. Another one, social security number, the same idea. Passport number, your address must be unique. And also, let's say your computer, they have some physical address over there. That's also unique. No computers have the same physical addresses. Okay? You kind of get an idea. Okay, that's a map. Any question about the map before I go on to show you some implementation? Okay? Yes, go ahead. Yeah. Okay, yeah. Save that for later. Okay, let's say this. Let's say we want to support some Java class which will support the construction of such map. The keys are going to be integers, and the values are going to be string. We got integer, we got strings. How do we support that? So let's say we have some assumption over here. Let's say the maximum capacity, which means the maximum number of entries you can store in the map, will be up to 100. Let's assume, okay? The user will never try to insert more than 100, okay? Just make it simple. Let's try a naive solution, okay? The naive solution there, and then I'll present to you the code, and then meanwhile, you can also illustrate very nice preparation for lab test 2. So now, even though I call it naive, it's not trivial. So you're expected to also understand that. But we'll go over in details. Okay, so I'm going to give you an idea now, but I'm going to show you the animation in just a moment. So now, this is what I'm going to do. I'm going to use the iPad here, and then show it to you. So now, is it visible, the diagram? Okay, first of all, I'll go over that with you. So now, this is something you can think about. Before you try to code up the Java, think about what's going to happen at the runtime. You can reverse engineer back to the code from your ideas. Let's try that for this class. Okay? So now, I'm going to guide you through what's going to happen. First of all, let's go back here. Imagine that this map over here is going to be called M. So at the runtime, we're going to have some objects called M of type map. And then it is going to consist of eventually 1, 2, 3, 4, 5, 6, 7 entries eventually. We're going to add one by one. But now, how do we do that? By just using a primitive array. Of course, using array list will be very easy. You can feel free to do that. But let's see the challenging part, how you can use an array. Okay. So now let's go there and see that what's going to happen. Okay, let me just guide you through, first of all, the initial stage. So now we have a map, which is called M. So M stores the address of some map objects. So let's just call it ArrayMap, which means we're going to use a single array to implement it. Okay? So there are 2 attributes over there. The first one is called entries. Entries is going to be declared like this. It's going to be entry over here. Entry is a class, which I'll define in just a moment. Entry, and then like that. So this is a declaration inside the array map, okay? Which means we have an attribute called entries. Its type is going to be an array of entry objects, right? Let's see how that's going to work. And then you can see this link over here is m.entries using the dot notation, okay? Now, this attribute over here is critical. It's called NOE, that stands for the number of entries. Initially just 0. When we first create a map, we're basically going to create an entry to be an array of size 100, since we assume the maximum capacity is simply 100. And now, since in the beginning we have no entries in the map just yet, so which means every slot in the array is going to be null, every slot. And how do we know that the array? How do we know that the map is empty? We always look at this attribute here, NOE. Okay. So now here is how things are going to work. Let's just try one thing here. Okay. Now let's say this. The first entry I would like to put, according to the table, 1 and D. Okay, this is a method call. Remember in lab number 2, you try to look at the use of some API, and then you kind of go back to the class definition for that. We're doing exactly the same thing. Okay, so now let's say this is how I'm going to use the map. I would say that n dot put, and then 1 and D. So this, I'm going to put some entry into the map. The key is 1, and the value is D, like that. I'm going to show you how to implement this in just a moment, but let's understand what's going to happen in the diagram to understand the behavior. Okay? So now I want to, again, emphasize there are several things you have to, there are 2 things you got to understand about this NOE over here. So NOE, I will write it down here. It has 2 purposes. NOE tells you, okay, actually. So NOE tells you 2 things. This attribute here. First of all, the number of entries in the map. This one is easy to understand. The second one is slightly trickier. The second one is NOE, you can think of it like a pointer. Because currently the value is 0, right? You can think of NOE as pointing to the first slot of the array, which is null at the moment. You can think about that as tells you the position of the next slot in the array to store a new entry. Which means if I want to add a new entry into the map, and wherever NOE is pointing to, that should be the place to go. In this case now, NOE is currently 0. That means we should store the new entry into position 0. Of course, you're going to increment that whenever you add a new entry. Let's see how that's going to happen. So this is number 1 over here. I say m.put 1 and D. Conceptually, it's very simple. First of all, we got to create an entry object. Let me create it over here. Entry over here. Entry. And remember what entry contains. Key and value. Okay, I'm going to say K and V. In this case, we're going to say the key should be 1 and the value should be D. And what's left is we should know where to really store the address of these entry objects. As I said before, the NOE tells you the next slot to be stored. In this case, we're going to do the following. We're going to say now, the 0 slot used to be null. It's not going to be null anymore. It's now going to store the address of this new entry. So it is going to point to here. At the same time, we want to say NOE has to be incremented from 0 to 1, because now we have 1 entry rather than 0. And then next time, if you have a new entry to be inserted into the map, you must go into 1. So that's the first insertion into the map. Any questions? Just conceptually, I'm happy to show you the code. Huh? The last statement? Okay, sure. Let me use a let me use a highlighter here. Before the insertion here, you see we're doing this insertion here. Before that, the map is simply just empty, which means the NOE over here is simply 0, which means it used to point to over here, used to. That means we have 0 entries in the map, and the next one you want to store will be at this particular slot, right? So that's why after we create this object here, we have to make sure we store that the address of these entry objects into this particular slot over here. After that, you got to make sure you update NOE, right? You got to make sure, because the next one to be inserted will be position 1, and the next one position 2, and the next one position 3. So far so good? Let me show you some animation. I hope that will show well in the projector, and then I'll just do one more with you. Hopefully that will carry forward the ideas. So now, hopefully that will show well. I really hope. Okay, that's the initial map. After the first one, second one, see where the NOE is moving. Third one, 4, 5, 6, 7. Should I do it again? So you can also watch that even though the pointer of NOE is moving from left to right, that's just conceptually. But what really happened in the programming is we are trying to increment the value of NOE. So it's as if you're moving the pointer from left to right. Let's do it again. Initially, NOE points to 0. And after inserting the first entry, now NOE has been incremented to 1. After inserting the second one, NOE is incremented to 2, and etc. Okay? So now for this particular map, we got 7 entries. That's why after that, you can see now the NOE is simply 7. If we want to insert another one, it will be inserted at position 7 of the array. Okay, I'll take questions before I, yeah. Raymond, yeah.
Just go back to the ArrayMap.
Yeah.
For entries, we initialize it as an array.
Yeah.
Should we set the size of it as well?
Yes, definitely. So you can see somehow, yeah, I see your point. Because you haven't seen the Java code yet, so I want to show you conceptually. Remember the diagram I showed you initially? So you can see that I already got the array. So that's after the constructor has been performed on the map. So we're going to create a fixed size array. Every slot is going to be null.
Okay. And so put changes the entries in order, right? So it goes 0, then 1, then 2, and
yeah.
If we wanted to change 6, we could just randomly change 6.
Well, I would say in this case, let's just make it simple to say every time you want to put a new entry into the map, we just go from left to right. Okay. Yeah, if you really want to have some customized order for your map, feel free. But I would say for this one, let's keep it simple. Questions? Right, right. Very good question. The question was, let's say, in this case over here, I already put 1 and D. Let's say the second entry is going to be 1 and E. The same key, but it's a different value. Remember what I said before, for a map, the keys must be unique. In this case, I'll leave it to you as your exercise. That should be a precondition violation. Agree? And you know what? This one will be a little bit trickier to implement. Actually, when you see the source code, it's actually say that exercise over here. I can give you some idea. Let's say whenever you're trying to put a new entry into the map, you have to run a loop to actually see to see all the entries existing over there. No key is equal to the new key. Okay, that's kind of the idea. That's something you can try. Okay. How about we do just one more before I move on? I just want to make sure everybody is okay. And when you actually read over the tutorial documents for point and point collector, that's exactly the same idea, the same. Okay, so make sure you understand this. Okay, let's do one more. Okay, let's say we got number 2. I'm going to use a different color here. What about pink? Number 2. Let's say we want to insert a second one. Let me just go back there. Second one is going to be 25 and C. Okay. So now I would say n dot put 25 and C over here, right? So now you can see that, first of all, currently NOE is 1. That means it's only one entry before I do the insertion. And if I want to do an insertion, position 1 is where to store it. So first of all, I'm going to create a new object of type entry. And then it has key and value here, 25 and C. So now, first of all, The current value of NOE tells me where to store it. I'm going to say m dot, I'm going to give you some idea, m dot entries at position NOE. In this case, NOE is simply just 1. In that case, that will be assigned to the address of this new object here, like that. Okay? In that case, what this will do, rather than pointing to null, it is going to point to over here. That's only part of the story, because you have to update the NOE. Otherwise, for the next put, you'll suffer. So what I got to do is increment the value from 1 to 2, which means now the current number of entries in the map has become 2. And if you want to insert the next one, it's going to be position 2. Okay? Any questions? You can feel free to complete the other 5 insertions yourself. Yeah.
So what if I add 100 entries? So I want to add one more.
It's a very good question. So you can think about, yes, very good question. Remember I put the assumption there to say its maximum capacity is 100. So now it can be another precondition violation. So let me just put it here. So there are 2 possible precondition violations you might have for put. One is when the key already exists. And the second is when you're already got 100 elements there, but you cannot add another one. Okay, already here. I will encourage you to try this as an exercise. Okay? So there are 2 preconditions for the put. The first one is the key already exists. That's number 1. And number 2 is we already reached the maximum capacity. The maximum capacity, in which case it's 100. Okay? Any questions before I ask you a question? Okay? Now, I'm going to ask you a question here. It's actually very important. Let's say I want to print out every entry in the map. Okay? I'm going to suggest one possible loop to you. Tell me if that's right or wrong. Okay? Let's say I want to print out the entire, let me keep the diagram here. I'm going to write it here. If I simply say for, let's say integer I is assigned to 0, I less than m dot entries dot length, and then I plus plus. And then inside, I just do the printout. Okay? So I want you to focus on this condition here. 1, 2, and 3. Is this for loop correct or not? Is it clear, or should I write it on another page? I want to make sure it's clear. It's readable. Huh? It's clear. Okay, good. Okay, I want to make sure. The length of the array, in this case, 100. Right? So is this right or wrong? What? Right or wrong? If there's one scenario where it can go wrong, you should say it's wrong. Well, what about in this scenario here? Exactly. So now, I want to make it even more obvious to you, so I think I would better have a new page. This is really important. Because if you got it wrong, you're going to have null pointer exception. You have no idea how to fix it. Okay? So now again, let me just say that. So m dot entries is pointing to some array over here, right? So let's say currently NOE is equal to, okay, let me make it a little bit larger. NOE is equal to 2, in which case we got 2 entries, okay? I'm just going to draw conceptually over here. And everything else is simply just null, all the way to null. And that's 99. The loop I wrote before was like this. I say for integer I is assigned to 0, I less than m dot entries dot length. And then I plus plus. Let me just write a little bit more. I can say print line. I can say, for example, m dot entries, which is an array, I can go into position I over here. I'll just pay that, and then I can say dot get key. Let's just say that, okay? Just make it easy. So now, the original question, can this go wrong? You want to try again, please? Can this go wrong? Yeah, just repeat your answer, maybe.
Yeah,
How can it go wrong?
if the array is in full, then you have no entries.
Yes, exactly. Well, to be more precise, in this example here, when I starting from 2, in which case it's already null slots, right? So now let's make it explicit. When I is 0 and 1, that's okay. But when I gets to 2, you will get trouble. So let's say when I is equal to 2, in this case, you're really talking about this null slot over here, which means over here is going to give you null. You're going to get null pointer exception. Okay? Okay, first of all, let's understand why this is wrong. The second question is, how should we fix it? NOE. Minus 1? Well, if you do minus 1, it's not going to, no. NOE, oh, I heard NOE minus 1, that's interesting. If I put, for example, over here, think about NOE is currently 2, right? If I say NOE minus 1, it's going to be 1. I would say I is equal to 0, I less than 1, which means only print out the very first entry, but you missed the second entry, right? So the correct answer should be, as you guys said, it's going to be m.e. Oh, sorry, m.moe. Okay, that's the answer. Okay, that's subtle points when you see the code. Yes? Yeah. Oh, if you want to find element, we'll get there. We'll get there. Exactly. Exactly. So we'll see how inefficient it could be. We'll see that in a moment. Okay. But I think so far, I just want to make sure it's intuitive to you. Of course, you still have to study the code a little bit. But I thought maybe giving you some intuition will help. Okay. Any questions before I move on? Okay. If we're okay, I believe that's this is now time to show the code. Let me just go back to my slides. Okay. Okay, let's see some code very quickly. The code is actually not too bad once you understand the concept. So now, first of all, we have a class called entry. And in entry over here, we only got 2 attributes, key and value. That makes sense. That's as I drew in the diagram. And we got some constructor here, which will be key and value, and then, okay, it's normal. And getters and setters for key and value. Okay, you can just define that yourself. Okay, or you can use Eclipse to generate that for you. Okay, now let's see the ArrayMap. That's a critical class. So now remember what I said before, we have basically, so here I'm just, as a good practice, I simply just say the maximum capacity is a final, is a constant, which is 100 at the moment, right? And then there are 2 attributes there. One is called entries, the other one is NOE. No surprise, right? 2 attributes there. Now, first of all, let's see for the constructor. So Raymond, back to your questions. How did I initialize the array? I simply say entries, when I first created ArrayMap objects, is assigned to new entry and then maximum capacity. That's why you got an array of size 100 with all the null slots. Okay? And then over here, I just explicitly assign NOE to be 0. It's not that necessary. If you leave out this line here, NOE, since it's an integer, you'll just get its default value 0. But you know, making that explicit doesn't hurt. Now, the next method there I'm going to show is size. So now, this hopefully will also strengthen your understanding. Because the NOE is private, but what if the user of the map, they want to know currently how many entries are there? You can just return NOE. Okay? And then the next one, how about the put? Okay, now you will see exactly what I show in the diagram. First of all, we're going to create a new entry object here using the key and value. And then we're going to use the current value of NOE, which tells us where the new entry should go, and assign the new entry E into that particular slot. And then we got to update the value of NOE by moving the pointer from left to right. So that's exactly what I show in the diagram. Are we okay? Good. Yes, go ahead. Yeah, of course. It's not given to you, right? Mm-hmm. Yeah. So you really have to know this pattern here, but it's not difficult. Okay, so if you want to know about this pattern more, please do read the reading. Okay, that one is already written down for you in detail, so you really want to follow. Okay, so now let's see a little bit test very quickly. So let's say we got an array map, and now I'm going to show you the other method you talk about, which is to find. How do we find? We'll implement that in just a moment. First of all, we have array map, and then it's a new array map. In the beginning, the size will just be 0. That makes sense. And then let's try to put the 7 entries from the table there. I can say put 1, the key, and string d, the value, and etc. Put 7 entries there. After that, you will get m.size is equal to 7. That also makes sense. Now let's get to the critical method here. So put is okay. I can tell it's working. Now I want to somehow implement a method. It's called so-called a lookup method. I want to look up, given a key, for example, I say m.get, I give a key over there. If the key already exists, it should return back to me the associated value. In this case, because I first put 1 associated with d, so now if I say get 1, that should give me back d. Okay, that's what this assertion is doing. Are we following? Okay. And similarly, if I pass 7, that should give me q. On the other hand, if I give some non-existing key, that will give me null, because 31 is not there. Okay? Good? Now, let's see how we can implement this get value method. And once we understand the code, we will get to the critical issue, why it is not so ideal. The get value here is going to take some integer key, returns the associated string value. And let's see. So you can see that, so when we specify the loop, it's going to be less than NOE, right? Not the length of the array, of the entries. Okay, we already explained that. So now for every entry I'm looking at, I'm going to assign that to E. And then I'm going to say the key is going to be E.getKey. Of course, I'm being a little bit verbose here. You can simplify that if you want. So now, if the current key I'm looking at is equal to, because they are integer, so I can use equal, so that's fine. If the current key I'm looking at is equal to the argument key I'm trying to find out, if that's the case, I'll simply return E.getValue, just return the associated value. Okay, let me give you some idea here. Let me just go back to the diagram there very quickly. Let's say over here, we got 7 entries there. Let's say I want to say m.get 39, the last one. What is going to happen? For the first iteration there, the key I'm looking at is 1. 1 is not equal to 39, so I'll go to the second iteration. And also the key I'm looking at in the second iteration is 25, which is not equal to 39, so I'll go on until I see that now 39 is really equal to the one I'm looking for, so I will return the associated value, which is C. Right? Now, maybe you have already seen or envisioned what the drawback can be for this kind of implementation. We'll get there. We'll have discussion. So now, first of all, before we discuss, any questions about this implementation here, about the get method? The return null over here simply because if we never get a chance to return the value, that means the key does not exist. We have gone to the end. Questions? Oh, we're good. Yes? So, say your question again. I'm not sure you really understand. Okay. First of all, there are no duplicates for the keys, right? So you can never have 2 keys which are the same. However, different keys might have the same value. Okay? Let me just give you, that is certainly okay. For example, let me show you here. Back in 1090, did you learn about functions, relations? You learned about, I'm not sure 1019 or 1090, okay? Do you know what's the difference between a function and relation? Right? So basically, if you say there's a function there, that means, well, basically function is like a mapping, basically. Whenever you're giving a key, it has some unique value to be mapped. So that's function. For relation, it's not necessarily the case. Okay? So now, so map is really a function. So this is what a map is. Okay? So for example, over here, I'm just going to draw conceptually. If I already got 1 and D over here, of course, I cannot insert another one, let's say 1 and E. I cannot, because the key will be duplicated. However, I can do something like this. I can do maybe another key 7, which is not duplicated, but I can just do the same value. That's okay. So this is absolutely fine. It's just that the keys, which will be used for search purposes, cannot be duplicated, but for the value, it's okay. Okay? Okay, now let's go back. If no questions about this code, let's now get to the critical part. Yeah? No. So key themselves can be any objects you like, as we'll see. So for now, for simplicity, I just make key the integer. Similar for value, it can be anything. Yeah. So that's why actually just a little bit look ahead. So when you try to use the hash table library class in Java, they simply say K and V. I'll show you that maybe next time. Maybe don't have time today. That means K and V can be any objects over there. Okay? Yeah, questions? Never mind? Okay. Okay. Okay, now, guys, let's discuss. Yes. Put method, yes. Very good question. So as I said, that'll be your exercise. Yes, yeah, because also it's a practical concern. I cannot fit in so much code in my slides, right? Yeah. Yeah, I gotta finish that, please. Yeah. Okay. So guys, when you download the source code, you will see exercises there. So you really want to try. You can either try it outside the lab test, or we can try inside the lab test. It's up to you. That's quite obvious, right? Good. Okay, now let's go back to the getValue method over here. Let's now discuss why it is correct. There's nothing wrong with it. It will work. However, it wouldn't be so realistic. Let's see why. So now let me use an example to give you some intuition. We wouldn't talk about it mathematically today. We will do that maybe after the reading week. So now let's say we got the map over here. We got 7 entries here. Okay. Now, how efficient is this particular lookup? Let's say I want to say m.get1. How many iterations should I run before I return? Just one, right? Wow, that's the best case, really, right? You found it right away. Very good. 1 iteration. Now, similar question here. How efficient is m.get7? Well, it happens to be 7, right? It's the last entry there. Okay, now, let's now think about a little bit more general. What if the m is already full, which means we have occupied all the 100 slots? In that case, let me make it also general. If I give you any arbitrary key k, what's the worst case? 100 iterations, right? Depending on the size of the entry array, right? You might be lucky, but I'm talking about worst case. You have to worry about, when you try to plan ahead your solution, don't think about best case. Best case usually doesn't happen. Usually doesn't, okay? The worst case, 100. Now make it even more general. What about I got 1,000,000 entries there? Well, actually, you know what? 1,000,000 is not even realistic. Think about we try to store the let's say citizenship record for Toronto, or for Ontario, for Canada, right? Well, how many iterations? Well, exactly 1,000,000, right? So do you notice something here? Because the way we try to look up the record here is very naive. We simply go from left to right. As soon as we find it, we return. But in the worst case, we may never find it. Or it might be that the record we want to find is sitting at the end of the array, at the rightmost. So now, there's some theoretical term for that. I will just tell that to you, but we can elaborate that a little bit later. So now we say that the worst case for this method here, somehow is the performance is linear. Linear in the sense that the worst case is going to be within some constant multiplicative factor to the size of the entries, which means in this case factor is just 1, which means the worst case can be just the same as the size of the entries. If there's a million, it's going to be a million. If there's a trillion, it's going to be a trillion. So that's really bad. Okay? Now, a much faster and also correct. So now you just don't just aim for speed. If you aim for speed, just print out hello world. It's the fastest you can do, right? A faster and correct solution is possible. What is that? Hash table, right? So now let me talk about any questions until now. So kind of move from the naive solution here, and so we're going to talk about hash table. Okay, now let's talk about the idea of hash table. I would say this slide here is going to be the most tricky one, so please make sure you ask questions about this one. Once you get this through, everything else hopefully will be much easier. So what's the idea about hash table? Let's try to use this diagram here to help you, but I'm going to just use the iPad, so that'll be easier. Okay. So now let's talk about the idea of a hash table. So now we talk about hashing. Hashing is actually a process. Okay, I'm going to talk about hashing exactly now. So now let's say you were given a key, K. So K, let me use a different color. I want to be consistent with the slides. Let's say we have a K. So this is the key we would like to search. In the naive solution, we might get linear time, right? We're just going to get the number of iterations that's proportionate to the size of the array. So now let's say this is the array we are talking about. Let me use a different color here. Let's say this is the array, which can be arbitrarily large. So we don't want the naive solution. So now we want to say, so let's think about what's cheap. What is cheap? There are two things that are cheap as a hint, as a motivation. There are two things that are really cheap computationally. That is cheap computation, there are two things. And that's exactly how the hash table were motivated. The first one is arithmetic. For example, if you say, if you say k is an integer, let's say, if you say k modulo 11, if you simply perform this operation, it's very cheap. Okay, it's a simple operation. And the second thing that's very cheap is array indexing. As I said before, array indexing, for example, if you say, let's say this is array A, capital A. If I say A go to a particular index I, it will be very cheap, right? It's like basically like a memory lookup directly. So now we're going to the hash table idea, basically just these two ideas. What's the first one going to do for us? We're going to somehow massage the k into some integer value. And the integer value, which is called hash code, which you're going to do for your lab 1. And the hash code, what's so magic about it? The hash code can be used as an index into the array A. Okay, let me just show you the process. There are two processes here. First of all, so there is a process called hashing. Okay, and by the process of hashing, we're going to somehow do some computation. So let me say HC, standing for hash code. Hash code is something you have to define, or you can use Eclipse to generate that for you. But let's just make it simple. You're going to have some hash code function. Let me say hash code over here. It's going to be a function. You will take some key and then return some integer. Okay? And in this case, I'm going to take the k over here as an input. It's a computation. So this one over here is very cheap, because we know that arithmetic usually is very cheap. That's arithmetic. So once we calculate this value here, hash function taking k as input is very cheap. It'll give you some integer. I can use this integer to index into the array, which is also very cheap. In that case, I'm going to do the indexing here. Now, let's say it happens to be here. Let's say this element here is simply array A, and then I'm going to pass HC of k. So this is the second part that's very cheap. This is the second part, array indexing. Somehow we transform our problem there. You see, let's compare the two solutions here. In the naive solution, we simply use the key verbatim. So that's why I'm going to do a linear search from left to right. But now we kind of do something very smart here. we try to convert the original key. And the key itself does not have to be integer. Just in this case, it happens to be integer, just for illustration. In general, it can be any objects. As long as you can define some hash function HC, you can turn your key into some integer. And the integer can just be used as the index of the array. In that case, computation of the hash code is very cheap. Using that index and go index into the array is also very cheap. So everything is cheap. Right? Does it make sense? Yeah. You know, in some way, saying that's cheap is very informal. I'm going to quit using this word starting from after the reading week. Okay. Let me just preview. We're going to say that these two operations, they are cheap because they are constant time operations. I will explain what constant time is after the reading week. Yes? HC is a method. Somehow HC, you know, so far I haven't talked about Java. I talk about mathematics. HC, but in Java it's called hash code. Okay. Yeah. Any questions before I move on? Okay, we're okay, right? Okay. So now let's move on. So now you will see this table here, exactly what I illustrated. So let's just go over that very quickly here. So given some numerical or non-numerical key, you can see the key doesn't have to be an integer. And then you can apply some hash function, HC, and then HC applied to k is going to return an integer. So hash code function always returns an integer, always. And the integer can be, it's called hash code, and the integer can be used as a valid index into the array. Okay? It must be a valid index, otherwise you'll get exception, in which case it's not correct, so there's no use if that's fast. Okay, so now we're going to say, and also once you calculate the hash code, you can use that to go into the array. That one is also very cheap, constant time operation. Okay, both are fast. Okay, are we okay so far? And then next slide, I'm going to make sure you understand this slide conceptually, and then I will show you some concrete example for hash code. Yeah.
I have a side question. Will this work if
Huh?
will this work if the key is on string?
The key can be anything, but just for this particular example, key are simply integer.
So I'll just ask if it works on the side.
Oh yeah, of course. You know, as I said, it can be any objects. Can be string, can be person, can be scanner, can be anything. Mm-hmm. Good question. So for the purpose of this course, there are only two choices you have. Either we give you a formula explicitly, in which case I will give you that choice. I'll tell you how to calculate a hash code. You only have to translate that arithmetic into Java syntax. You're given the instruction. The second is, if you really want to generate some hash code for your complicated object structure, use Eclipse to do that for you. I will show you also how you can do that in Eclipse, these two options. But in 2011, you will learn about different strategy of doing that more sophisticatedly.
Are we storing the data, like indexing it with the hash code?
Indexing with the hash code, but we still store the data in the array under the hood.
So we are like initially storing it, the index position should be the
Hash code.
hash code.
Yes, correct. Yeah, correct. So let's see some concrete example. Hopefully that makes even more sense. Let's say the array we have is simply of size 10. Make it very simple. Let's say this is my hash function. Taking the key k as an integer, I'm simply going to calculate k modulo 11. Okay? So now, let's go back to our original table over there. So now, we used to have 1, 25, 3, 14, 6, 39, and 7, right? They used to be the keys. So now, look at on the leftmost column. They are the corresponding hash codes for them using this formula. For example, 25 modulo 11 would be 3, right? You agree? And did you notice that some things that might appear strange to you for the hash code?
They're not unique.
They are not unique? Very good. However, for hash code, it doesn't have to be unique. That's the tricky bit. The keys have to be unique, but the hash code that's generated from the keys may not be unique. This is an intuition. In practice, you might have 1 million entries into your array, but somehow your array cannot be arbitrarily big. So when you want to generate a hash code, then you might have some duplication in the hash code. It's something called collision. You just have to know the word. You don't have to know the theory. Okay? I'll just give you some concept over here. So that's a very good observation. So your search keys cannot be duplicated, but your hash code can be. That's okay. Okay, another way to think of it is you can think of the hash table as some called bucket array. You can think of each slot over here is storing a bucket conceptually. Okay, so now for example, I'll give you one example right away. You can look at in the case of search key 25, 3, and 14, they calculate it into the same hash code 3. In that case, we're going to store the same. Going to store the 3 entries in the same bucket that is mapped by hash code position number 3, right? Okay. So now you can see that over here. Okay. Does that make sense? Bucket. Okay, because the hash code can be the same. So something called collision, which means you have unequal keys, but they generate the same hash code. That's okay, practically. However, a good hash function should really make sure you minimize the collision, and also to make sure there's no particular bucket that's too big. In which case, let's say this. Let me give you one example here. Let's say I want to say m.get 14. m.get 14. Now 14 is the key. I cannot use 14 to directly access the array. I cannot, it's out of bound. I gotta calculate the hash code that's corresponding to 14, which is 3. If I go to index 3, I don't really see the entry with key 14 right away because it's a bucket. So I still have to look through from left to right in that particular bucket. So it's kind of proportionate to the size of the bucket. But as I said before, as I said over here, a good hash function should really make sure the sizes of each bucket should be uniformly distributed. That's something that's really subject to some complicated hash function, which you don't have to know for this course. You may have to know for 2011.
By changing modulo 11 to different numbers?
You can certainly try to play around with different numbers. I'm just trying to show you one case over here.
But
Yeah.
like I'm saying you make it uniformly distributed by changing the 11?
Yeah, you can do that. Yeah. In this case, I simply do a very naive strategy. It's usually just modulo the size of the array you're given. Okay, that's one strategy. Yeah. Okay, so now let's go on. So now let me go through. So far, I haven't shown you any hash code, right? But I will in a moment. So once you understand the concept, I think everything will be okay. So now I want to show you this is the most important principle you have to know. Which means let's do a little bit of 1090, shall we? Oh. I really want to teach 1090 actually. I really want to. That's a fun course. Anyway, you're gonna retake it if I teach it? No, it's okay. Don't worry about it. Okay, let's focus on that. So over here, I have an implication. That means if K1 and K2 being keys, if they are equal, that means their hash code must be the same. That's the only principle you have. Which means the same keys must have the same hash code. Okay? Now, you learned something about in 1090, right? That's exactly what I want to. What's contrapositive? If I say P implies Q, what's contrapositive? Not Q implies not P, right? So I said this is the principle. You can have a look at it in another way. So which means if the hash code are not the same, that means the keys cannot be equal. Okay, just another way to look at that. Okay, it's not too bad, right? Okay, good. Okay, that's the number one principle. Think about it. That's the number one principle, the only principle you must have. Okay, let me just, I can finish Java code in just 3 minutes, okay? So now how do we do hash code? Let's say I define a class called integer key, and that has only one integer attribute here, and then very easy constructor here, and now hash code. I'm going to override the hash code method. I'll show you in the beginning of Tuesday how you can do that. Okay, and hash code simply return k modulo 11. Okay, that's exactly what I did. And then something to note, also for the equals method, every time you define hash code, you must also define equals method properly. Otherwise, they have to work together. Now, one question for you to think about, we'll answer this on Tuesday. Can we simply define the equals method as this the hash code equals out of the hash code? Think about it. Don't answer me now. Think about it. Okay. And now this is how you can test the hash code. For example, I got the 1, which has hash code 1, I got 39, which got hash code 6. And then you can make sure the hash code is really the same. Right? You can look through the test. Okay? One more thing, please. So now, test hash table. This is why we are doing hash code. Hash table has been implemented for you as a library class. However, whenever you want to use hash code, make sure the key you pass over there has already defined its hash code method. That's the most important thing to notice, right? So now, you can look through that code, and then let me see anything else to mention. You can look through that. You can see the only thing that's required for you to know for 2030 is only this slide, only this one. But the reason that I mentioned so many things, I think it's better to have the complete story, okay? Okay, so I will see you next Tuesday.